Welcome back. Today we'll discuss about magnetic dipoles. In the last video lecture, we have discussed about magnetic potentials and we have already seen how to compute current density due to magnetic potentials. In this class, we will discuss about magnetic field and how to compute magnetic field due to a magnetic dipole. So I think you have already studied this magnetic dipole in your plus 2. So let's have a quick recap about this magnetic dipole. A magnetic dipole is a magnetic north pole and a south pole which are separated by a small distance. Normally you see all the bar magnets, they'll be having both north and south pole. Whereas in electrical, the charges can stay isolated. But whereas in magnetic, particularly the bar magnets, they do not stay isolated. So most of the times you can find these north pole and south pole together, which we call it as a magnetic dipole. It is also characterized by a dipole moment, what we call it as magnetic dipole moment, which is nothing but magnetic dipole moment, which is the torque experienced by this material when it is placed in a magnetic field. So we will write it as the pole strength and the length of magnet. The length of magnet is nothing but it is the separation between the poles. So this is the way how we determine the magnetic dipole moments. Now let us suppose we don't find always all the bar magnets everywhere in our electrical engineering. So in the last classes we have seen that any current carrying conductor can develop a magnetic field. So now let us suppose if there is a loop which is carrying a current, then the magnetic dipole moment is the product of the current and also the area of the loop which it is covering. So whatever the direction, if it is normal to the loop, see the magnetic dipole moment direction is always normal to the loop. Now let us suppose this is the current and this is the surface area which is covering. So magnetic dipole moment is always normal to this one. So it will be in this fashion or in this fashion depending upon the direction of the current. So if I is the current flowing in the loop of surface area S, so magnetic moment is normally represented by the letter U, which is equal to I into S into U. Okay. Now let us suppose if there is a dipole. Now see here, I will assume that there is a dipole which is present, and in particular I will consider this dipole to be a circular loop of radius A and carrying a current of I. So this is my loop, current carrying loop, which is carrying a current in this fashion I, and it is having a radius of A. This is a radius A. Now the magnetic vector potential, we have already seen these things. So let us suppose if I take any point here, at this point the magnetic potential is given by, this is the magnetic potential. We have already seen in the last classes. At this point, if I consider this spherical coordinate systems, I'll take it as capital R. So if this is the magnetic potential, capital A, then it is defined. Normally we know that the equation, right? It is mu I dl by 4 pi r. In this case, this is a spherical system. So these are constants. So that's why I'll take it as over the length, it is dl by capital R. This is my A. Right. So this can be written as this I over the entire length. It can be taken as M star. by 4 pi r square. Integral of r is 1 by r square. So this is my magnetic vector potential due to a current carrying loop. Now let us suppose if the magnetic moment of the loop is given by pi a square into uz. Okay. So converting the magnetic moment of cylindrical Cartesian coordinate systems into spherical coordinates. We know that this is here, right? This, right? So it is 0, 0 pi a square because it is in z direction. So if I convert it into spherical system, this is my expression. So I have converted into spherical system, and now I am replacing it. B is equal to del cross A, right? A was already in, we have applied, right? A is equal to u I by 4 pi. We have taken this. So we have already tried this one, right? So it was mu m u r bar by 4 pi r square, right? So this was in Cartesian coordinate systems. Sorry, this was in spherical coordinates, right? So I am going to apply this one. So UR is already in spherical coordinates. This is M, right? So M was in, actually it was magnetic dipole moment, which was equal to pi into pi a square into az. I have taken it as in the z direction. So I need to convert this one into again spherical coordinates. That's what we tried in the last slide, right? This was the last slide. I had only pi a square z component. So I'm converting this one into xyz into spherical system. So this was what the equation which I have got. So if I substitute it here, m, this is my m, right? Right. So if you see, this is my expression. So ur cross ur, you will get 0, and u theta cross ur, you will get u phi, and minus pi a square sine theta. So you will get minus will closed. So this is my expression for B. If I do this one, del operator in spherical systems. So this is my del operator. We have seen how to apply this cross product in the previous class when we were doing magnetic potentials. So similarly, in cylindrical system I have applied, and this is my expression for magnetic flux density, where A is the radius of the circle and theta is the angle which is made by the point of the center, and r is the length from the center to the point which we are considering. I hope that now you are able to apply this equations for determining the magnetic flux density due to a current carrying loop. Okay, so this is the problem. Determine the magnetic moment of an electric circuit formed by the triangle shown below. Okay, so that's it for today. We'll solve the problems in the classroom.